Welcome. In this video, we'll explore the gauge fixing of the Bosonic BFSS model on the lattice. Our goal is to see how the continuum BFSS model is discretized, gauge fixed, and how the holonomy and Vandermonde determinant naturally lead to the Faddeev-Popov contribution. The BFSS model contains 9 bosonic Hermitian matrices, X sub m, and 16 fermionic Hermitian matrices, psi sub alpha, plus the gauge field A sub t. The full action, shown in equation 1, has 4 parts: the kinetic term d sub t x sub m squared, the quartic commutator potential, the fermionic kinetic term, and the Yukawa coupling with gamma matrices. Equation 2 defines the covariant derivative d sub t, which appears in the kinetic term. Equation 3 gives the boundary conditions: bosons periodic, fermions antiperiodic. Integrating out fermions produces the Pfaffian of O of x and A sub t, where O is the Dirac operator. In the quenched approximation, this is set to 1, leaving the bosonic truncation in equation 5. Equation 6 shows the t-Hooft limit: n goes to infinity, g goes to 0, with lambda equals g squared n fixed. This is the limit in which this matrix quantum mechanics describes quantum gravitational effect. Moreover, in equation 7, we show the scaling of the various objects: x as inverse length, lambda as inverse length cubed, t as inverse length. Thus, we can argue that the only dimensionless coupling in the model is lambda tilde equals lambda over t cubed, shown in equation 8. Thus, we can set lambda to 1, or 1 over g squared equals n. The only physical parameter is therefore given by the Hawking temperature, T, which equals 1 over the period beta. Time is discretized as T equals NA, where A is the lattice spacing, and with beta equals lambda times A. The gauge field along one step becomes a link, the path-ordered exponential u sub n, n plus 1, which for small a is approximately 1 minus ia times A sub t, as shown in equation 10. Using these links, the covariant derivative becomes a gauge covariant finite difference. Transport x sub m forward with the link, subtract the local value, then divide by the lattice spacing A, as indicated in equation 11. Local u of n gauge symmetry acts on fields and links, so this finite difference stays covariant, which is shown in equation 12. Putting everything together gives the bosonic lattice action in equation 13, a kinetic piece, a nearest neighbor coupling built from the links, and the quartic commutator potential, preserving the BFSS structure on a time lattice. Using the gauge symmetry, we absorb links into the fields and define x prime sub m of n by multiplying with the chain of links from 0 to n. That's shown in equation 14. In this rotated basis, the action simplifies, nearest neighbor terms remain, and a single special term appears that involves w, as shown in equation 15. The matrix W is defined as the product u sub 0, 1 times u sub 1, 2, up to u sub lambda minus 1, lambda. Equation 16. This matrix W is the holonomy, the parallel transport once around the Euclidean time circle. On the lattice, we can concentrate this holonomy on the last link, from lambda minus 1 to 0, so all other temporal links are effectively gauged away, while W carries the global information around the circle. Next, we diagonalize the holonomy, W equals V dV dagger, with D the diagonal of phases e to the I theta sub I as in equation 17. Rotate correspondingly the fields to x tilde sub m equals V dagger x prime sub mv, and obtain the final lattice action with holonomy on the last link, equations 18 and 19. This is equivalent to static diagonal, or Polyakov gauge, where W equals xp of minus I beta A sub t, giving a diagonal gauge field shown in equation 20. Here, the holonomy sits on the final link. However, we can also distribute it uniformly among all links using d sub lambda, the lambda t root of d, with the final action given in equation 21. Finally, W itself isn't gauge invariant. The Polyakov loop is p equals 1 over n times trace W. Its expectation value is the order parameter. 0 means confined, non-zero means deconfined. Now we reduce the measure. Using gauge invariance, we collect all temporal links into the holonomy W, then change variables W equals V dV dagger, where D is the diagonal matrix of phases e to the I theta sub I. The Jacobian is delta of d squared, the Vandermonde determinant familiar from random matrix theory. After integrating out the remaining links in V, the measure reduces thus to the eigenangles theta sub I with this Vandermonde factor, as shown on this slide. Next, we write the Vandermonde explicitly. Delta squared equals the product over I greater than j of absolute e to the I theta I minus e to the I theta j squared, which equals the product of 4 times sine squared of half the angle differences. Hence, the reduced measure becomes product d theta times xp of minus s sub fp, with s sub fp equals minus 1/2 the sum over I not equal j of log sine squared of half the angle difference. This is exactly the Faddeev-Popov term. Final takeaway, the total action is S equals S sub B plus S sub Fp. S sub B is the gauge-fixed bosonic lattice action with kinetic and commutator terms and the holonomy d diagonal e to the I theta sub I inserted on the last link. The eigenangle measure yields S sub Fp minus 1/2 the sum over I not equal j of log sine squared of half the angle difference. Together, S sub B and S sub Fp define the gauge-fixed BFSS path integral.